Hello and welcome. In this video, we're going to take a look at what it means for a function to be continuous. Now, I could probably ruin this whole video and just sort of give a vague description that a function is continuous if you can draw it from left to right without lifting your pencil at any point in time and without crossing a vertical line more than once so that you still pass the vertical line test. But that alone isn't really a technical definition. It doesn't really help you necessarily understand what continuity means. So we're going to start off with what it means for a function to be continuous at a single point. And then if a function is continuous at a single point, we can say it's continuous for all points in an interval and start talking about whether a function is continuous over an interval or not. So to start things off, we're going to take a look at what it means for a function to be continuous at a single point. And a function is continuous at some number a if the limit of that function as x approaches a is equal to the value of the function evaluated at a. Now, this equation alone has a few implications. The first implication from the left-hand side is saying that the limit of f of x as x approaches a is definitely equal to a value. It does exist. So we can list that as sort of the first implication here. The limit of our function f of x as x approaches a exists. Now from that implication, there's something else that we can imply, and that's that the left-hand limit and right-hand limit must both equal the same value. Now another implication is from looking at the right-hand side, f of a. That would be undefined if a wasn't in the domain of f. But because we have f of a as being a number in this equation, that can be our second implication here, is that a is in the domain of f. Now, taking a look at this graph I've drawn here, implication number one says, as I'm approaching a from the left and from the right, you can see that the y values should be approaching some value. They both seem to be approaching the same y value. And you can get as close to that y value as you wish by choosing x sufficiently close to a. The left-hand and right-hand limits both agree with each other. Now, the second implication, f of a. A is in the domain of f. So you can see that also means I have a point right here that exists at the coordinates a comma f of a. Now, really the equation puts those two implications together and says that the value of the limit is equal to the value of f of a. And that is the third implication here. Putting all these together, that's what makes a function continuous. At a certain point, we're approaching from the left or from the right. It seems like we're approaching the same value. And at the coordinates where x equals a, the function is defined, and the value of the limit is equal to the value of f of a. So it's essentially, like I said, you're just drawing a line approaching a dot, and that dot, that point, does in fact exist. So it means you don't have a hole, and it means that your function doesn't have different one-sided limits. If one of these three implications here, one of those three statements is false, then we would have a function that has a discontinuity at x equals a. Now let's stop and take a little look at the different ways that a function might have a discontinuity. And we can actually categorize the types of discontinuities. And this is probably best to look at a graph. Let's start off with a function where maybe the limit exists. So as I'm approaching a, let's assume that the limit does exist. I'm coming in from the left and I'm coming in from the right, and it does seem to be approaching the same value. But then what about if I make the second statement false, that a is not in the domain of f? Well, then I'd have to draw an open hole here. And so that ends up being a discontinuity. And the only way to draw this is really to sort of lift the pencil. You have a line going over to close to the a value, a line coming from the other side close to the a value, and they don't meet in the middle. So that's where we have a hole. Okay, so that's one kind of behavior. Another kind of behavior that's very similar to that is, let's assume the limit does exist again. So we can draw the same, more or less, where let's say that the limit from the left here and the limit from the right are both approaching the same value. Let's assume that statement 2 is also true. and a is in the domain of f. Okay, so I'm going to put a solid dot somewhere along this dotted line. There is a point that exists somewhere at the point where x equals a. But I'm going to make statement 3 false. I'm going to assume that the value of the limit, so from the left and from the right, they're approaching a number roughly around this red dotted line. And I'm going to say that the value of f of a is not the same. Let's say f of a is somewhere up here. So I'm going to have a point on my graph way up here. That means I have to have a hole down here. That's also a discontinuity. Sure enough, the limit exists. A is in the domain of f, but the value of the limit is not the same as the value of f of a. Now, both of these kinds of behaviors we call a removable discontinuity. And the way I like to think about a discontinuity of this kind of form, the way it's called removable, it's just kind of like it's a pothole in the pavement, and you can patch that up. So all I really have to do is if I could just take this dot here, and if I could just move it down, suddenly I don't have a discontinuity anymore. And in this other example, if I just added an extra point, and I just make sure that I take that point and I lower it down into that hole, I've filled the gap and it's now fixed. It's now a continuous function. So that's how I like to think about a removable discontinuity. It's just imagine it's like a pothole that we can fix. Rather than calling it a fixable discontinuity, it just means that we can remove the discontinuity. Now, one of the statements that we haven't broken yet is the first statement. What happens when we get a discontinuity that's caused by the limit not existing? And there's a few different circumstances where the limit might not exist. Again, let's draw a graph here. Let's assume that the limit doesn't exist. There's a couple of reasons why that could happen. First of all, the limit from the left might be different than the limit from the right. So they're pointing at different values. The left-hand limit seems to be approaching one value. The right-hand limit seems to be approaching a different value. Well, right off the bat, even if I put f of a in the domain, let's say a is right here, and there's the point a comma f of a. And as a little note, of course, they couldn't both be solid dots. The other one would have to be an open dot. Well, it's definitely not a removable discontinuity. There's just no way that I can take this point here that exists on the graph and move it somewhere to fill this entire hole. This isn't just a pothole. This is a broken bridge, and that isn't something I can just easily remove in a day by patching it up. I need to build an entire new bridge. I need a new function. So, what can you do with a broken bridge? Well, we can take a sweet jump off one side and land on the other side, right? Think about it that way. This is what we call a jump discontinuity. Coming off the left-hand side, this is just a big ramp, and we can jump onto the function from the right. Don't try this from the right-hand side. You'll just fall into a pit. But the idea is right there. It's essentially what happens when the limit doesn't exist because of the two sides being different values. That's a jump discontinuity. And there's one other reason why we might have the limit not exist. And that's actually when sometimes we actually say that the limit equals infinity, it means that we've got an asymptote. So the limit from the left, the limit from the right, both seem to agree in this example. And we would say that at the value a here, we've got the limit, let's call this function f of x, the limit as x approaches a of our function equals infinity. But that's not a number, right? That's just a concept. That means that the limit doesn't exist. It doesn't equal a number. So it's not a continuous function at that point. There's no way that we can have f of a equal infinity because that's not a number. That can't happen. This is kind of similar to a jump discontinuity, but it's a little bit more specific. So we might call this one an infinite discontinuity. And it is also quite possible that an infinite discontinuity is a jump discontinuity as well. It's very possible that from the right we go to positive infinity and from the left we go to negative infinity. And that's a jump, right? You're going up this crazy steep ramp on one side and you can try landing on the track from the left. But it goes up to infinity, so it's a little different than a normal just jump discontinuity. Better to call it an infinite discontinuity. All right, well, a lot of functions that we look at don't have this kind of behavior. But let's look at a couple functions where we actually do have discontinuities. And they come up sometimes in trig functions, and they come up frequently with piecewise functions. All right, here I've got a piecewise function f of x. And there are 3 different rules defined for different intervals of x. We've got one interval where x is less than 0, another interval from 0 to 3, but including 0, and another interval greater than 3, but including 3. And because we see a lot of very nice functions here, we probably can imagine that there's not going to be discontinuities. But we do have the potential where one function meets another that we might have jump discontinuities or removable discontinuities. Let's see what kind of discontinuities we might end up with here. And you can see that when the functions end, the different pieces might connect. Let's try and see what happens as we get closer to x equals 0. And that'll be our first analysis, is looking at whether or not this is a continuous function at x equals 0. First of the 3 statements is, does the limit exist? And because the functions are different on either side of x equals 0, we need to look at the left-hand limit and the right-hand limit. Now, if we look at the limit as x approaches 0 from the left, then we know that x is going to be slightly less than 0, and we're going to be only having to look at the function 3x squared plus 1. So we can then say, well, we need to take the limit of 3x squared plus 1 as x approaches 0, because we're very, very close to 0, just a little bit less. Now, of course, this function is a very nice polynomial, and it's defined at 0, so we can plug 0 in, and we get plus 1. Now it's time to look at the right-hand limit. Now, from the right-hand side, just imagine that x is just a little bit larger than 0. In that interval, we'll be between 0 and 3, in which case we're going to be looking at the function 2 minus x, and then taking the limit as x goes to 0 from the right here. And of course, that is a polynomial, and it's defined at 0, so we can plug 0 right in and say that equals 2. And right off the bat, since these values are different, we can conclude that the limit as x approaches 0 from the 2 sides does not exist. And right off the bat then, we can see that this is a jump. From one side, it looks like our function's at a height of 1 unit, and from the other side, our function is at a height of 2 units. And that leaves this 1 unit jump from one piece of the function to another. It doesn't matter, but we can continue on and even also just take a look, just for the sake of doing this, just as an example, we can see that f of 0 is actually defined. F of 0 is equal to the second piece here, 2 minus 0, which is just equal to 2. So, okay, it is actually defined, but the limit doesn't exist. And you can imagine that this behavior means that we've got some function from the left-hand side, must be a parabola, so maybe something like this, and it's got an open dot. And from the right, we've got a line, so maybe you can imagine a solid dot and a line sloping downwards. You can see it's a jump right there. But if you wanted to be a little bit more specific, from the right-hand side, it would kind of look like it was being continuous, right? On the right-hand side, the function is approaching the value of the function. So if you want to be a little bit more particular on this one, we can actually add a little note here that this is continuous from the right. And it's more or less the same definition, except we see that the limit as x approaches a from the right of a function equals the function of value weighted at a. That's what it means to be continuous from the right. We just changed the definition slightly so that we're only looking at a one-sided limit. But it's definitely not continuous from the left, because as we approach from the left, we're approaching an open circle, and that means that it's not approaching f of a at all. Now, the definition for being continuous from the left is essentially the same, but it's a one-sided limit from the left-hand side as x approaches a with a little minus sign. Not continuous from the left, but this one is continuous from the right. We find another value where this function f of x might have a discontinuity. Well, we can see we've got a nice straight line between 0 and 3, and we've got a horizontal line, the line y equals -1, for x greater than or equal to 3. So there might be a potential there where the two different segments of the function don't connect. And we should check out and see what kind of behavior we have at x equals 3. We'll repeat this process by looking at the left-hand limit and right-hand limit as x approaches 3. Okay, now the left-hand limit, if we're approaching 3 from the left-hand side, that'll put us in the interval from 0 to 3, in which case we'll be looking at the function 2 minus x, and we'll be taking the limit as x approaches 3 from the left. That function is defined at x equals 3, and it's just a polynomial, so we can plug that in and we get -1. And we can try the same thing from the right-hand side, and if we approach 3 from the right-hand side, we'll be in the interval for x greater than 3, in which case we're just looking at the function -1. And that's a constant, so the limit of a constant is just equal to itself, -1. And that means that the two-sided limit does in fact exist. The limit of our piecewise function as x approaches 3 from the left or from the right is equal to -1. Now it just remains to check and see if f of 3 is also a value that's equal to that limit. And f of 3, we'd have to make sure we have the correct line, is the bottom one up at the top here of the screen. It is simply equal to -1 as well. And by the definition, we have the limit as x approaches 3 of f of x equals f of 3. We can check that off and we can say it is continuous at x equals 3. Now, if a function is continuous at 3, then it's also continuous from the right and from the left. So just like limits, if a limit is defined for the left and the right and they're equal to each other, then the two-sided limit exists. Well, if a function is continuous from the left and continuous from the right, then we must know it's continuous. And vice versa. If a function is continuous at a number, it's continuous from both sides. Now, we're going to extend this just slightly. Now that we know what it means for a function to be continuous at a number, if a function is continuous at every single real number in an interval, then we can say that the function is continuous for that entire interval. So it's just another little definition, but more or less just an extension of being continuous at a single value. So very simple. Function f is continuous over an interval, I, for instance, if f is continuous at every number in that interval I. And due to the limit laws and knowing that most functions behave well with limits, we can actually kind of extend that a little bit and we can talk about what functions are continuous. And that becomes a great theorem, and we can talk about all of the main functions that we're looking at in this course and where they are continuous. We'll put that into a theorem here. And this theorem, we will just leave it unnamed, but it's still important. It's just not necessarily a theorem that you'd have to recall for a test situation necessarily. So the following functions are continuous at every number in their domains. Let's start off with one of the most basic kinds of functions, polynomials. If we wanted to divide one polynomial by another polynomial, we get a rational function, and those are continuous at every number in their domains. If we wanted to combine polynomials with some roots, some radicals, we can get radical expressions, and those are continuous at every number in their domain. Then we can start getting into exponential functions. And if we look at the inverse of exponential functions, we have logarithmic functions. And then we've also looked at trigonometric functions and the inverses of trigonometric functions. Now, you might be thinking, hold on a second, I definitely know that tangent is a trigonometric function and it has discontinuities. And wait a second, logarithms have a big asymptote as well. They have a discontinuity. And what about radicals? I mean, you can't even take the square root of a negative number. Well, that's where this part here is much more important than you'd think. It's in their domains. They're saying that, yeah, logarithmic functions aren't defined for negative values, but then they're also not continuous for negative values. Not defined at 0, but that's okay. It's not continuous at 0. It's continuous for numbers just a little bit more than 0. If you think about the function y equals the natural log of x, for instance, it definitely has a big asymptote. And that would maybe trigger you and think, okay, that must be an infinite discontinuity. But it's not. Here's our function y equals ln x. and its domain is the numbers from 0 to infinity. So that means it's not continuous at 0. It's only continuous for the numbers slightly bigger than 0 up to infinity. And that hopefully makes a little bit more sense. Well, what about radicals? Let's take a look at y equals root x. Or better yet, let's make this a function f of x. Now the root function also doesn't end up being defined for negative values, but it is defined at 0. Kind of looks like a sideways parabola, but only half of one. Now its domain includes 0. So now, does that make a lot of sense that this function is continuous at 0? It kind of does, but only when we consider that it is continuous from the right at 0. It can't be continuous from the left because the function is undefined for negative values, but we say that it is continuous from the right at 0. And by extending our definition of continuity to being continuous from one side, then it makes a lot more sense. Now, the last thing just to talk about is with continuous functions, limits are very easy to evaluate. Continuous functions, the limit is going to exist from the right and from the left at numbers in its domain. And then we can also take a composition of continuous functions. If we have continuous functions, then we can compose them together and get another continuous function. So we'll end this video with one more theorem here that will help to evaluate limits of a little bit more complicated functions other than just polynomials and rational functions. For this theorem, we're going to start off with two conditions. One is that f is continuous at some number b, and two, that the limit of g of x as x approaches a is equal to that number b. Then, as a consequence of those two conditions, if we ever find ourselves having to take the limit of a function f with another function inside of it, g, and we know that the limit of g of x as x approaches a is equal to b, then we can go ahead and we can take the limit of the inside, find the result is b, and because f is continuous at b, we can simply evaluate the outside function at b. And this may only be useful in a few scenarios where we have odd functions that we don't look at very often, maybe things like inverse trig functions that we normally wouldn't be taking the limits of. So, for example, let's suppose we've got our function as arctangent or inverse tangent of x squared minus 2 over 3x minus 4. Well, I know that the domain of arctangent is all real numbers. It's actually a pretty nice function that way. And it's continuous at every value in its domain by the last theorem. So no matter what the value of the inside function, x squared minus 2 over 3x minus 4, whatever the limit of that function happens to evaluate as, I know that I can just evaluate arctan of the result. So by both theorems here, we can just go ahead and say that this is equal to arctangent of whatever we get for the limit of x squared minus 2 over 3x minus 4 as x approaches 2. And by a theorem in our previous videos, we can see that this is a rational expression and it is defined at x equals 2, so we can evaluate that limit and see what we end up getting simply by plugging 2 right in. 2 squared minus 2 over 3 times 2 minus 4. And that leaves us with 2 in the numerator, and it leaves us with 2 in the denominator, and so this is arctangent of 1. And thankfully, due to a special triangle in quadrant 1, remember, we can only get angles in quadrants 1 or 4 when we use arctangent. This is opposite over adjacent equals 1. So we could write the two sides as 1 over 1, and this is our 1, 1 root 2 triangle with an angle of pi over 4. So our answer is pi over 4 in radians. Okay, so that kind of gives you at least an idea of a few theorems, but the bigger point of this whole section, this whole topic here, is what it means for a function to be continuous. And we have another big theorem coming up here that I'll leave to another video. This particular theorem does in fact have a name. It's pretty important. It can show up in all kinds of places, even in much more advanced mathematics. we can talk about the intermediate value theorem. And so I'll save that for a future video. Stay tuned. Thanks for watching. I'll see you again later.